Hello, everyone. Hello. Sorry, the mics don't work too well, I think, projecting here. Okay, no, work fine. So we're going to get started. Thank you very much for coming. Welcome. These are the ICARL seminars, which today are, as always, sponsored by InstaDeep, Google DeepMind, and Iconic. And this is a very special seminar for us because this was a seminar series that popped up from reinforcement learning reading group. And as a bunch of reinforcement learning researchers, we all in the group initiated our adventures with a very nice book from the person who is now presenting today. So I think there is no need of any presentation. We're very happy to have today with us Professor Richard Sutton, who is going to be talking about dynamic deep learning. Richard.
Thank you. Thank you, Boy. It's really a pleasure to be here today and have a chance to talk to you, share some ideas with you. I've never been to Imperial before, and I've just learned about all kinds of interesting things going on here. It's all very exciting and it's impressive in many ways. So today, let's start with some general remarks before I get into really what I'm going to cover today. AI, artificial intelligence, is really ambitious. So what I would say that AI researchers seek to understand intelligence well enough to create beings of greater intelligence than current humans. Pretty awesome goal. I think reaching this profound intellectual milestone will enrich our economies, challenge our societal institutions. It's going to be unprecedented. It's going to be transformational, but also a continuation of trends that are thousands of years old. People have always created tools, technology, and been changed by it. This is what we do. It's what humans do. The next big step is to understand ourselves. This is a quest, grand and glorious, quintessentially human. Yeah, of course, it's also totally hyped up. But I don't think I'm hyping it here. The things I'm saying here are just true. This is a grand quest. But it is hyped up. It's not a good climate for science. You know, science likes things to be steady and calm and focus on the important fundamental issues, whereas AI is like there's a lot of money going into it. There is so many companies. There is people, arguing that what I'm doing is enough. You don't need to do anything anybody else. It's not. It doesn't feel. I don't know if you guys sense it, but I sense that it's not a really good climate for science. For example, large language models, really popular thing, really important thing, really powerful thing, but they can't just accept that they're going to be really important and really valuable. They have to say, oh, this is all that the mind does. The mind, they have to claim that large language models can do reasoning and maybe they're conscious and all kinds of crazy stuff. Instead of, because the real scientific attitude, you figure out what you can do and try to understand what you can't do and quietly make progress. I think we're not really, that's not really the culture that I feel in our field at the moment. So I think I'm just a little bit disappointed by that. But I don't doubt that it's an important question that we're trying to address. Okay, now some others of my perspective. So I'm one of these guys that are trying to understand and create maximally intelligent agents. And an agent is defined to be intelligent to the extent that it's able to predict and control its input stream, particularly its reward. This is the way I would define intelligence, not the way everyone would define intelligence. Not to pick on the large language models, but they don't actually try to predict and control their input stream. Technically, when they're running, they don't even have an input stream. So we want to control, we want to affect our input. And the creation of these super intelligent agents and super intelligent augmented humans, I think will be an unalloyed good for the world. I'm not going to say that the world is going to be an unalloyed good, thoroughly good. Because the future, I think, is going to be tough because we're in what's called a fourth turning. If you don't know what that is, you might check it out sometime. It's kind of an interesting set of ways of viewing societal change. Well, the path to intelligent agents runs through reinforcement learning, now through the LMMs. But the biggest current bottleneck to ambitious reinforcement learning-based AI is that our deep learning methods that we rely on are inadequate to the task. They're not well suited to the task. And that's what I'm going to talk about today, that they fail when we ask them we put them in a dynamic situation where they have to continue to learn. As you know, I think all deep learning methods, when they're deployed, when they're acting on a robot or interacting with humans, they no longer learn. They learn only in advance. They are sort of transient learning systems. Now, and one more sort of introductory slide, just to tell you where I am, where my thoughts are. And I just put this in like 2 minutes ago, actually. This is the standard architecture of reinforcement learning. And if you see all these components of a model-based reinforcement learning agent, that's what MBRL is, model-based reinforcement learning agent, takes in observations, emits actions, and it also takes in a reward. And it basically composes of 4 parts. Perception takes in the stream of events and emits a representation of the current situation or the state. Probably it's a feature vector. And then that's passed to the policy, the reactive policy to pick an action. And those two, right in the middle, these two, perception and action, those two together form a complete agent. But if you want the agent to be adaptive, and if we want it to be intelligent, it's going to have to be adaptive, as I have defined it. Then you're going to need a value function to say how well things are going, and then use the TDR from the value function to adjust the policy. So this diagonal line through the policy, if you can see that, represents not an informational transfer, like the state comes into the policy, emits the action, but the diagonal line means you're changing the function implemented by the box. Okay, so value function changes the policy. Now, at the same time, the full agent, a full model-based agent, you also learn a transition model, which is a model of the world and its state transitions, observing the states here. Here you see the state at a particular point in time, and you might notice the state at a particular point in time, and then you take an action, and then you find yourself in a new state after some amount of time, and that's a transition, and your transition model would model those transitions by observing the data, and then you can ask questions of your model. What if I did this action instead? What would happen then? Oh, yeah, I would take you to this state. Then you could apply the value function to that state, and you get a TDR. And then you could use that to adjust the policy again, and we call that planning, because whenever you're using a model and not experience to adjust your anything, we call it planning. These are just definitions of how I'm going to use the words. Now, in the full architecture, we have not just one policy and one value function, but a whole set of them. And that's meant to be suggested by these that are stacked up behind the true policy and stacked up behind the value function. We have more value functions. So that's where you would pose subtasks for yourself and you learn skills how to achieve other things other than the reward, while always being cognizant of the effect of those other things on the reward. Okay, this is just on the side, right? I hope it's interesting, but it's on the side. And a lot of this is developed in these papers that you might want to, it could be checked out. Okay, now let's get to today. Today we're going to talk about dynamic deep learning, but really it's about a paper that my colleagues and I wrote. And the title is helpful for clarifying the topic. The topic is loss of plasticity in deep continual learning. And I'll define all those things in a minute, but now's my chance to talk about me a little bit more. I acknowledge I have many jobs: Keen Technologies, the University of Alberta, AMI, the Alberta Machine Intelligence Institute, my own reinforcement learning lab, And Open Mind Research, I want to tell you about this a little bit. This is our logo. Open Mind is a new institute that we've created that's devoted to doing fundamental research along the lines of reinforcement learning, the Alberta plan, for people who have already graduated and obtained their degree, but want to do research in this area. And it's distributed. We have kind of a focus in Alberta, but it's distributed and people can be all over the world. And if you might want to do fundamental research in this area and you want to focus on that rather than become a professor, you may want to apply to be a fellow of our institute. Okay, now here's my main message. My main message is that deep learning doesn't work for continual learning. And by not work, I mean that learning slows and eventually goes to a very low level of learning. You've lost plasticity. And by deep learning, I mean all the standard artificial neural network methods, specialized as they are for this non-continual or transient learning. And I also mean without replay buffers, because I consider themselves an acknowledgement that deep learning doesn't work. Now, better learning algorithms that are specialized or well suited to continual learning, they're not hard to find and they can apply to deep learning. So I don't think there's anything wrong with artificial neural networks. We just need to find better algorithms, and we only need we have to start looking for them. And so that's my main message. And then this work details and substantiates this claim. Okay, so I'm going to have demonstrations of loss of plasticity in deep learning, and the attempts to maintain it. And this will be in classic supervised learning problems like ImageNet and CFAR 100 with residual networks, and also in reinforcement learning, but primarily in these classic supervised learning problem domains. You know now already that I'm not really a supervised learning guy. I'm aiming at reinforcement learning, but I need all those 4 boxes that I showed you. They all need to learn continually, because you live in your world and you keep adapting to whatever it throws at you, and you have to model the world, and the world changes. The world is infinitely complex. You'll never be able to anticipate all the ways it might change. And so you have to continually learn. And then hopefully I'll have just a little bit on some goals and ideas for a next generation of deep learning that would be well suited for continual learning settings. Now, this work has just been published in Nature, so I'm really excited about that. It's the first time ever been published in Nature. And but I want you to realize that even when you have a publication success, it's often preceded by a large time where you have publication failure. So this happens all the time. It's just if something's fashionable, you can get it published in Nature, right? If it's not fashionable, you can't get it published at all. Sometimes. I've experienced this many times. All of my best publications were really hard to get published. Temporal difference learning, when I published that, really hard. Options, almost. It's almost always true that the more novel and groundbreaking your results are, the harder it will be to get them published. So if you're having trouble, take heart a little bit and realize you'll have to persevere. And if you persevere, you may eventually get published, but it's not guaranteed. It may never become fashionable. So we in particular tried to publish this over like 4.5 years, and we're unsuccessful. You can see it in archive. Archive is good. Plasticity just means the ability to learn. And so loss of plasticity just means loss of the ability to learn, or not being able to learn continually, not continual learning. Hope you're getting comfortable with the way I'm using these words. Maintaining plasticity is maintaining the ability to learn. And so in AI, since we want all the 4 boxes to learn, we should prioritize maintaining plasticity. And we're not the first to see this problem, to see at least hints of the problem. It's very closely related to the idea of catastrophic forgetting, where in deep learning, you learn some things and you learn some more things, you often totally forget the old ones. Now, loss of plasticity is you learn some things, you learn some new things, maybe you learn some new things after that, and eventually you can't learn any more new things. It's not the same as catastrophic forgetting. It's sort of catastrophic loss of plasticity. So there are also hints of this in the early neural networks work in the psych literature. And there are a few works like Ash and Adams that showed the failure of warm starting. Warm starting was like you thought, oh, I'll teach this neural network on part of the data, and that'll warm it up so that it'll, give it the second half of the data, it'll be faster. But in fact, they found the opposite. If they trained it on the first bit, then it was slower on the second bit. And it was much better if they just put the two parts into one big thing and trained it all once from scratch. It was kind of surprising. It was surprising, seen as a failure. That was one of the earliest demonstrations. And primacy bias, Nikoshin, capacity loss, Claire Lyle and others. These are shown in reinforcement learning. Okay, but no one really did a thorough demonstration in supervised learning of this phenomenon, and because you have to do it thorough. It's a negative, sort of a negative result. If you get hints, it doesn't change people's minds. And so the significance of this piece of work was that we did it really thoroughly and dotted all the I's and crossed all the T's and considered all the possible ways you can get around it and have something that's pretty incontrovertible. Okay. So let me show you the first one of these demonstrations, loss of plasticity in supervised learning, and we're going to use the classic domain of ImageNet. So ImageNet, you have this database of millions of images, and they're like, this is an image. This is a shark. Hope that's obvious to you. This is somewhat downsampled, and we have to use somewhat downsampled images. But there are 1,000 classes, each with 700 or more images, and it's widely used. But we need to change it because it's widely used as a pure supervised learning problem. Like they take all the data, they train on all the data at once, and then they gradually freeze it. They train and train and train, multiple presentations, and then finally they freeze it. And actually, they gradually freeze it and slow down learning until they have a nice stable state. We don't want to do that. We want to have something that will continue to learn. So how are we going to do that? So we're going to make a variation of the problem, which is called continual ImageNet. So and we see it as a minimal change to the classic one. So we do the usual thing. There's 700 examples, remember, for each class. So we separate that into training, 600 training and 100 test ones. And then we take them in pairs. So like this might be the first pair. We'll show you crocodiles versus guitars. And you have to learn to distinguish those two. Okay, and then when you're doing, well, we've seen all the examples of those pairs. We go on to a second pair. Like, so think about how that's done. The network only has two options, two outputs, A or B, or yes or no, crocodile or guitar. And so then when you want to ask a new question, you add, well, since I'm never going to ask you again about crocodiles and guitars, I can actually throw out the heads, the final two neurons of the neural network, and replace them with two new ones for the new task. The new task is to distinguish game controllers from fish. Okay, and then once you've learned that, I erase the heads and give you a new problem: bow ties versus oxen, I guess. Okay, and this continues, and you can do many pairs because remember there's 1,000 pairs. So you might think I could make 500 pairs, but you can actually make many more because you can reuse ones as long as you don't reuse the pair. So how many pairs of thousands of things? It's like almost 1,000 squared. So you have lots of pairs, and we can do this forever. Performance measure is I'm just going to measure the percent that are correct on the test set. Remember, I present all the examples for the two classes, and then I have some saved out ones. I measure performance on them, and then I average this over many, many runs. And in the many runs, I vary the pairings of the class. You don't have to worry that maybe the first class is hard or the first class is easy, since they're all averaged over all the possibilities. Okay, that's sort of the problem. And then there's a whole other set of details for the learning network. And talked about how the heads are reset, the final heads. The structure of the network is pretty standard. It's a little bit narrow because we only ask it to classify two things at once. We don't want it to be infinite in its size compared to the things we ask of it. So it has some structure of convolution layers and interconnected layers. And notice the last one is just two. Those are the last two heads. Okay, and then we use batches, we use epochs in all the usual ways. Now, it's important that the weights are initialized in the standard way and that it's only done once. It's only for the very beginning, on the first task, before the first task, we randomize all the weights, small initial values. This is a standard practice. But it's only done once. When you start to get new data from the new task, you're not told it's a new task. And so there's no opportunity to reinitialize or do anything. And you maybe don't want to reinitialize. Think about it. Maybe you've learned one thing and now you're going to learn something new. Maybe what you learned on the first one maybe the features you learned on the first one will help you get the heads for the new task. Maybe they'll be able to do much better because they have better features. Okay, so we start with just plain backprop, momentum, cross entropy loss, relative activations, the usual things. And we of course varied all these things, but the standard case is this one. And yeah, many variations, get representative results. And then I want to ask you, how do you think, what do you think will happen over the sequence of tasks? Will performance be better on the first task or the second task? Are you voting for first? Elliot?
I think it'll improve and saturate.
You think it will improve, and since that would make sense. It should, maybe the second task will be better, third task maybe will be better, and at some point you're not going to get any more advantage from having learned good features. That would be good. That's the way a learning system should work. Okay. Okay. This is the beginning. I'm going to show you just the beginning first. And obviously it's going to depend on your, well, let me do the axes first. The axes are task number along the bottom, the first pair, the fifth pair. And this is percent correct. Okay, so and these are, well, what are you tuned for? This red line was tuned for doing as well as you could on the very first task. So it's sort of fast, right? And so that gets up to about 89% correct on the first task. This is slower. Remember the backprop alpha. Alpha is the step size. So this red alpha is 10 times faster than the orange alpha. Okay, with orange alpha, you, at least after a while, maybe you get up to a higher level. But this one's the fastest at the very beginning. Okay, does this all make sense? Okay, now the linear baseline is, well, what if you didn't have all this network stuff? You just took the pixels and you learned a linear map from the pixels to the class. That's actually not, you can do much better than random. What's random? Random is two classes, so it's 50-50. 50% would be random. Yeah, and actually, what else I mentioned? The shade region is one standard error. Linear baseline is performance of the linear heads. There's no non-linearity. There's just a single, well, 2 units. And so this doesn't have to be run actually with multiple tasks, because there's nothing to save from one task to the next. The 2 heads are replaced, the 2 linear heads are replaced, that's the whole network. So you don't have to run it many times. We have to run it many times, and we established that you could get 77% approximately correct with a linear system. Okay, so that's really poor performance, right? That would be bad because you're not even using all that network to do anything. Okay, so maybe we're improving at the beginning. This guy seems to be improving, but what happens in the long run? Okay, that's the real question. So this is what happens in the long run. And so These are this red and the orange are the same curves you saw previously, just extended. So let's go with the red one, which started out at 89%, which is this point, right? But this first data point is an average over 50, because there's, just for graphing purposes, to get rid of all the jaggies, it's good to average over the first 50 tasks. And so over that first 50 tasks, you really can only do about 84% correct, because you're already starting to decrease in performance. And then you see that playing out. As you go more and more tasks, you get worse and worse until you're performing worse than just a linear network. And if you use a different set of parameters, if you're slower, you also get worse and worse, and then you level out at just a little bit better than the linear network. This is an even slower step size, and it also does poorly. Okay, so this is one setup, but it's representative. We've seen this pattern over and over again. If you vary the details, you can get small variations in different shapes, but this is the pattern that you will always get. In the long run, you can't do better than the much better than the linear baseline. And also, if you introduce variations like bring in atom actually makes it worse. Dropout makes it worse. Many of these things just makes performance worse. Okay, so what's the summary? For good hyperparameters, plasticity decreases across tasks, nearing the performance of the one-layer linear network or worse. So this is what I'm calling catastrophic loss of plasticity. Question?
Do you have any explanation for why it is that with an alpha of 0.01, you keep seeing this catastrophic loss of plasticity, but that smaller alphas sort of level out and retain some baseline level of plasticity?
We haven't thought about arguing that the orange line is good. And you think the orange line is equally a failure. I've never asked the students who did this. All the students I listed, Shivansh, Dohare, and Fernando, all these about that particular question. I'm not sure I can answer that. Any other questions? Thank you. How do we explain how the brown line is definitely increasing? And as we saw, the orange line also, if we looked at detail at the first 10 tasks, it also was increasing. So that's what Alex called for, that we should get some improvement in the beginning. And so that makes sense to Alex. And the way we were understanding it was that you learn features during the early tasks, and those features are later are useful on the subsequent tasks. And particularly if you're learning slowly, then empirically we're seeing that if you learn slowly, then you're getting a much greater effect of that nature. You're getting savings across the tasks. What you learn, maybe it takes a while to find good features, and if you can only learn really slowly, then you get more accumulation over tasks. Okay. So there are better algorithms. As I said, things like dropout and standard variations make things worse. But there are a few. This red line is the same line we saw before. We've just rescaled it. He's going way down low. But if you have a good algorithm, you can show improvement. So this is shrink and perturb and L2 regularization. L2 regularization just means you add something that encourages the weights from getting too big. You prefer small weights, and so this keeps them in a labile range, so they can keep training, keep learning for more experience. And I'll show you some details on that in a minute. Shrink and perturb does L2 regularization, but it also does a random perturbation of the weights. And so these two are good. We're going to repeatedly see these are good at partially solving the problem. And continual backprop is our own algorithm. And it's basically just like backprop. It's following gradient descent. But in addition, we select just a very small proportion of the units, and we select the proportion that are least useful to the network, and we reinitialize them. So like less than 1 unit per example, very small fraction of them. And we have a utility measure, so we can measure their utility, how much they're contributing to the network's behavior. And if the ones that are used least will be candidates for being reinitialized. And that small change solves this problem.
I have a question online about how do you select? I guess.
Yes, I'll talk about that in a minute. Let me just postpone that. But it's a measure of its utility. And as you'll see, many of the units are not useful at all. This is a phenomenon of backprop. Okay, and maybe I have it here. Continual backprop, stochastic gradient descent with selective reinitialization, just like backprop, except reinitialize. This is our only parameter with the rate at which we reinitialize. I said it's very small, very slow. That is a hyperparameter. And we show that it's better to reinitialize selectively using a measure of utility. So for example, shrink and perturb also makes random changes, but it doesn't do it selectively. It's always just taking all the weights and wiggling them around a little bit. And this is an old idea. It's really sort of a kind of generate and test. We're keeping the units that are contributing to the network, and we are taking the ones that are not contributing, and we're going to randomly vary them. And this idea existed before. Rupam Mahmood and I did some work on it. It goes back to the 60s, like Oliver Selfridge did Pandemonium, and it also was like this, generating units in a network. And the thing about continual backprop is it extends the idea to general multi-layer networks. Okay, so I want to show you, in some sense, convolution networks are old school, old style. Now we want to do residual networks, which also have many layers, like 18 layers, but we also have shortcut connections or cut through connections. So you don't it's not strictly layered anymore. This is more modern architecture. And we're also going to change the problem a little bit. We're going to use CFAR 100, and we're going to present five classes, and then we're going to progressively add more. So we're not going to like before we had pairs, another pair, a different pair. We just did different pairs, same number. Now we're going to add, we started with 5, then we'll add 5 more, so we'll have 10. So this is the old 5. We're still going to present those, yeah, and we're also going to present the new 5. And the next we'll present this 10. We'll keep presenting all of that 10, and we'll get 5 more, so there'll be 15. And we just keep going until you get all 100 of them. Okay. Now, if you think about that, the second task will be harder than the first one, right? The first one just has 5 classes. This one has 10 classes. Next one has 15 classes. So you expect overall accuracy to go down over time. And so you can't measure overall accuracy. If you want to see a loss of performance, what we use is we show performance relative to a network that's trained from scratch with the same number of classes. So say you had 50 classes, you could just reinitialize your network, give it 50 in the old way, the 50 are all presented at once, and that'll perform a certain well. And then you could do it in this incremental way, where you get 5, 10, 15, 20, so far up. And what will it be? Will it be after you get to the 50, will you be performing worse or better than if you see them all at once? Does the progressivity help you or hurt you? Okay. And what we find is the y-axis here is the difference between these two. Did you do better or worse? Because you're presenting them incrementally. Got it? Okay, so what we find is that, yeah, there's a definite effect of you do better by doing it incrementally at the beginning. You gain a couple percentage points of accuracy, which is quite a significant effect. And then it decreases, and if you do usual backprop after about, I don't know, 40, 45, it's neutral. And then you get this loss of plasticity effect, where you do much, much worse than presenting them all together at once. Shrink and perturb isn't quite as bad, but it's bad. You're losing plasticity, and with continual backprop, you're able to maintain the same level. You get exactly what Alex asked for. You get an improvement at the beginning, and then you plateau. Okay, so that's the general pattern.
Yeah.
Yeah, good.
Because you said you keep the same performance in the long run with continual backprop, but at least are you able to reach that performance sooner than with a network that has been trained from scratch with all of them at once? So is the learning time at least faster with continual backprop than when you, because we're trying to see the advantage, right, of just throwing all the data at once to a network learning.
Well, all the methods are getting an advantage in learning time at the beginning. Right, that's what we see.
Yeah, that spike, but at the end.
At the end, there is, and then we're measuring performance only on the full set.
Yeah, but my question then is like, since performance is the same, did you notice that continual backprop was reaching that performance sooner than network learning from scratch?
I don't think there is any measure of sooner. You mean once you're, say, presenting all 50 of them?
Yeah, I mean, with a good
So in the progressive case,
yeah,
you've been presenting them in smaller groups all along. And so for most of the classes, by the time you get to all 50 of them, you've already learned a lot.
I would expect to be faster, but I wanted to confirm if you.
Well, you'll get, 45 of them pretty well at the beginning. Remember, the performance measure is at the well, actually, I didn't say what the performance measure exactly is here, and maybe I'm not sure, but I am sure for the previous example. The previous example, and I think we're doing the same sort of thing, is we present things and then we have this test set. So we finish learning and then we measure performance. So there isn't a speed within the group. You know what I mean? Yeah.
What I was asking is, for like the number of classes 50, for example, when
Yeah.
you train the network from scratch on 50 classes,
Yeah.
you present as many examples to that network as you present to the network that is doing the
Yeah, it's definitely the same number of examples.
So in that sense, it is slower because it has seen 49 times the training set size plus
No, the total is the same.
the total is the same
Yeah,
for the one that is trained.
yeah, yeah. Is that right?
And I understand the question now.
Yeah. Maybe I'm not sure. But this I think you'll find interesting. Here we're looking inside the network and trying to figure out what's happening. Okay, so as we increase the number of classes, this graph is showing the percentage of units that are inactive, that are dormant or dead. Which means they're defining that as active less than 1% of the time. And so you start out with small random weights, everyone's active. I guess active means they're ReLUs, remember? So if the activity is less than 0, they're capped at 0, floored at 0. And so active means their activity is greater than 0. And at the beginning, they're going to be greater than 0 half the time. And so none are active less than 0% of the time. And then as we train, just for standard backprop, Yeah, actually, I should have said that. In this experiment, if you do standard backprop, you don't even, it does, you don't perform, it doesn't work at all. You have to already use L2 regularization. So that's why in these experiments, we don't show you results for L2 regularization because everything is using L2 regularization. That's needed. Okay, so anyway, that base learning system gains up or has increasing numbers of dormant units, more than half by the end of 100 tasks, 100 classes, and shrink and perturb does much better in terms of many fewer dormant units, and continual backprop has hardly any. And we also measured the diversity of the representation, which means often you have features that become similar to one another, and they don't add anything to the linear rank of the you measure the number of I don't even know how to say it, number of independent components in the features in the network. And so we scale this between 0 and 1, and we can see like clearly that just a base learning system, we lose diversity, we lose the rank of the representation. And with some of the other methods, we can preserve diversity. Okay, now I tried to say, here's where I emphasize the robustness in these problems, and we've done other problems, we've done idealized problems, we've done MNIST, and shortly I'll be doing reinforcement learning. So across network architectures, across activation functions, not just ReLU, but a whole variety of them, and across the hyperparameters, we see that just plain the deep supervised learning loses plasticity dramatically in the continual setting. L2 regularization improves it, but just a little bit, and shrink and perturb often will help a little bit further. With the weight randomizing. Continual backprop does the best to maintain the plasticity. It has one hyperparameter, but as long as we're insensitive to that, it's just can be set very small. And so now let's go on and do finally reinforcement learning. So we're going to do ant locomotion. Maybe you've seen this problem. We have this ant. Don't I have some videos here? Let me scoop ahead. Yeah, some videos. So here's the ant on the right side, moving rapidly forward. The object is to move forward as rapidly as you can. This is an ant that's not moving forward at all. It's doing very poorly. This one's doing very well. And we're doing this, we measure the reward is forward motion, and the actions is to control these 8 joints where there are red marks. And this is a standard task. And here, the performance, we're showing the time steps. We're training for rather a long time. Often you will only train for 1 million or 2 time steps. We're going to go 20 million. And we're going to measure the rewards per episode, which is 1 trip of running forward as fast as you can. And then you're brought back to the beginning to run some more. And here we have a non-stationary problem, and that means that we're going to vary the friction between the feet and the ground. So every 2 million steps, we're going to vary the friction. We're going to vary it. I don't have a figure for that, but sometimes it's fast. Sometimes the feet are sticky, and sometimes they're slippery, and so it changes the nature of the problem every time you vary the friction with the ground. So these actually I call this an alligator graph because it looks like the back of an alligator's tail. You're doing well, and then there's a switch in the problem, and your performance falls, and then it recovers, falls and recovers. And so let's first look at the standard reinforcement learning algorithm, PPO. It does well at the beginning, but then at a certain point it plateaus. And if you just keep training, it degenerates. And your ant that used to look like this one, oh, I think I must have skipped this slide. Yeah, this was supposed to show the slipperiness. We're going to vary that. And here's our standard PPO performing well. But if we just keep going, it starts to end up looking like that second one. Starts looking like this guy. And performance is actually degenerates, so it's worse than how you started. And you can, so this is this, so people have seen this before, but you know, when this happens, they tend to just stop. They stop training early on. And if you stop training, you can avoid this fall. But a real learning system would be faced with that. Okay,
Ali online asking, could a similar effect be seen if mass was changed instead of friction?
Excuse me?
Could a similar effect be seen if mass was changed instead of friction?
Yeah, we believe so. We have every reason to believe so. As long as there's something, well, actually, I guess I should move a little more quickly.
Yeah.
Because I'll answer that in the next slide. But yes, this quick answer is yes. Okay, now if we tune the learning algorithm, we can do better, but we still see a drop, a loss of plasticity over time. And as before, L2 and continual backprop can largely solve the problem, Now, I want to show you this one. This is the same thing, except there's no changing in friction. There's just regular ant, okay? And but reinforcement learning does involve changes. It always involves changes because the policy gradually changes, and it involves temporal difference learning. Temporal difference learning, the targets are always changing. So really, even without changes, even in a stationary problem, you should get this. We get this effect. We realize later we get the same effect, and performance just drops. And this is where I say, well, why doesn't everyone see this? Well, they do see this, and they just stop training after a few million. They because arguably it's okay. You're just interested in a good policy. You can stop and use that policy. But if you want to keep learning, it's a big problem. Now, if you tune your parameters, you last longer and you get higher, but still you suffer and you lose all your plasticity. Regularization can maintain it, and continual backprop can maintain it better. Okay, so here now we'll take a closer look inside this algorithm. And again, we look at the percentage of dormant units, and those are increasing to more than half. L2 and continual backprop, keeping it low. Stable rank is the same pattern. And here's a new one, the average weight magnitude. If you just look at the units and look at how big the weights are. And with standard backprop, the weights are getting bigger and bigger and bigger. There's nothing that forces them to be small. And maybe that's the full explanation. Just the weights get bigger, and so they're harder to change. L2 regularization forces them to be small, and maybe that will interfere with performance. And so that gives some insight into what's going on. So conclusions: deep learning networks are optimized for one-time learning. In a sense, they totally fail for continual learning. And these simple changes like continual backprop can make them effective for continual learning, where you're going to rank units by the utility to the network, preserves the most useful. So I guess I never got into the details of utility. And I guess that's because I don't think the specific way we rank them, we don't think it's necessarily the very best. In fact, that's one thing we're working on now, how to do it better, in a better way. What if your network is recurrent, or what if right now we're using a fairly local measure. We have the units, each unit is looking at its outgoing weights, and if the immediately outgoing weights, if they're all zero, for example, you're not useful. But some of them may be large, but you don't know that you're connecting to someone your large weight is to a unit that is useful, which would be necessary in order for you to be useful. So that we're still experimenting with that. I think there's a large, exciting world ahead of deep learning networks can learn continually, and particularly it opens up new possibilities for reinforcement learning, which is inherently continual. And model-based reinforcement learning, where you have all these different components that are interacting, and all of which are learning simultaneously and continually. Okay, so that's my completion of the demonstration part. And now let me just say a few, I could say a few words about ways we're going to try to solve these problems further, but it's a good time for questions right now.
There are a few online actually.
Yeah, good.
So one very linked to what
You were presenting was what will happen for continual backprop without the L2 regularization.
Well, it is necessary in these later problems to make it work well. So it wasn't in the first problem. So I don't know, it just doesn't perform as well in some cases. Yeah.
Chris Wu as well asked, what kind of advantage continual learning can gain over the normal deep learning?
Well, it's really a change in the problem, right? We're asking a continual problem where, well, I guess in backprop reinforcement learning is always continual. What's the advantage? I guess, didn't I just show that? Didn't I just show that if you have a changing problem and you need to do continual backprop or regular backprop?
Totally.
Okay, let's just go to in person.
So just to wrap my head around application a bit more and just kind of hopping back to their queries on efficiencies of like baseline training, say on like, n number of tasks versus like n-5 to n tasks. I understand that in the supervised setting, the advantage may be more for like fine tuning or something like this, where you have like some existing model and you want to add new tasks or something like this.
Yeah, so like if say we're doing large language models and we train them up, and then like another week's information comes out on the internet, new news stories, and you'd like to have your large language model be up to date with the new news stories, that's a big problem nowadays. And what they actually do nowadays is when they update the models infrequently, because every time they update them, they have to clear out the whole network, the old network, they clear it to scratch, start over from small weights, and they train all the data at once. They have to start all over again. You'd like to be able to just add the new data.
And like the reinforcement learning context seems like a lot more it's even from like from initial training, it seems like it's better because reinforcement learning is a lot more continuous in nature. So it seems like in the supervised setting, fine tuning is like sort of this key application because that way you don't have to waste old models. Whereas in reinforcement learning, it's kind of a new paradigm of training. Does that make sense?
Better say it more concisely.
Sure. So in the supervised setting, it seems that fine tuning sort of, to me, it seems it's more of the main application because if it's.
In both cases, you need continual learning, really.
So just going back to their question, if its accuracy is the same as the baseline, with continual learning and with, that baseline number of tasks, what's the sort of notable advantage unless you use like less compute in the continual learning setting?
I don't get it.
Flexible number, you can always increase the number, the other one is one fixed number, no?
Sure, yeah.
In real life, you will always have more numbers coming in. So
Yeah, but if you're adding more numbers, that's a fine tuning task, right? If you're adding new tasks later on after initially training a base model.
Are you suggesting that fine tuning is an alternative to continual learning?
Well, no, I'm just suggesting that for supervised learning, it seems like the continual backpropagation seems like more of the usefulness because if you're getting the same level of accuracy,
Getting the same.
as like, a baseline number of tasks. If you go back to the graph, right, when you have, say, 50 tasks, right, when you're comparing it to the continual backpropagation, the accuracy is about the same.
which I showed you're not getting the same level of performance.
In sort of the prior chart, right, on the supervised tasks, that's sort of what it looks like. This was just sort of like,
Maybe we'll talk later.
Sure,
I'm
sure.
obviously confused.
Thank you very much. Hello. Excuse me if this is a bit of a critical question, but in the evaluation of the where you add classes continuously, like you start off with 5 classes and then add another 5 and then so on. And you mentioned that you train for an equal amount of epochs, I assume. Could the deterioration of the normal backpropagation not just be explained by the fact that it sees fewer examples of the new classes?
Yeah, I guess I was unclear about that. I am unclear in my own mind exactly how that's done. But absolutely the intent was to do a fair comparison. Neither one would have more data. And yeah, I guess I'm not clear how that was done. Sorry about that.
No worries, no worries.
What happened to the utility of the recently reinitialized weights? You said you reinitialize them based on lowest utility.
Yeah.
Do the recently reinitialized ones jump in utility or stay low?
This one I can answer. When they're reinitialized, when I say they are reinitialized in the standard way, but it's a little bit subtle, just a tiny bit subtle. We reinitialize the incoming weights to the new unit to be random in the ordinary way. But the outgoing weights are reinitialized to 0 because we don't want them to interfere with the current performance of the system. If the outgoing weights were non-zero, they would mess things up a little bit. This newly initialized unit, what will its utility be? Its utility will be 0 because it's outgoing what we call 0. Okay, so if we really rank strictly by utility, when you add a new one, that's the one you're going to throw away and reinitialize the next time. So we do need to keep track of the age of a unit and prevent a newly created unit that's very, very young from being replaced. Good job. Okay.
Where do you see research in deep learning and reinforcement learning going? Do you think the focus will be in modifying the backprop algorithm for the continual learning and reinforcement learning setting, like in this paper, or do you see it going somewhere else?
Well, what do we consider? It's continual backprop modifying the algorithm, the backprop algorithm. You know, it sounds like it is. It's an adjective onto backprop. Yeah, I think it is. It's the continual backprop is almost like more backprop. What is backprop? Backprop is you do initializing and then you do gradient descent. And we're just going to do initializing all the time, okay, as you go along. So it is very much in the same spirit. Maybe it's not a new algorithm. And what will happen in the future? Do we envision algorithms that are very different from continual backprop, or is that about it? And I think we need to go significantly beyond backprop and continual backprop for the best to achieve all of our goals, what we would like from continual learning. Because I want from continual learning, I not only want this bare ability to not lose all your plasticity, but I also want to do things like meta learn, improve the way I generalize. Special thing about continual learning is you learn some, and then you learn more, and then you learn more. So you have this experience with learning, and you can see the way I learned it this time, that worked out so. And the way I learned this way, it worked out a little bit better. You can evaluate how well your learning has gone. This is something you can't do if you learn in one shot. If you learn in one shot, you're just done. But if you learn and then you learn more and learn more, then you can learn to learn. Say this way of learning works better than that way. So if that seems too abstract for you, let me be concrete. how would you like to, would you generalize more on this feature or you generalize more on that feature? We'd like to learn that. We'd like to learn how to generalize. Modern deep learning systems don't really learn how to generalize. They're structured to generalize in a particular way, and maybe they were lucky and they've generalized pretty well, or maybe that's the skill of their designers. But there definitely is no algorithm that's causing them to learn well, and I think we want to have our algorithms learn to generalize well. So that's part of the ambition for continual learning. It's not going to come just from tweaking backprop. We have to add more things. And let me just use that. We can still have questions, but let me say a few of these things about the new ideas. We want methods that will learn continually, of course. We want to be able to learn nonlinear functions, of course, and we want them to be very efficient. But the last point is we want them to meta-learn to generalize better. And this is the slide I want to do. Ideally, a streaming deep learning or what I call dynamic deep learning should adapt to 3 levels. You should adapt the weights, that's the usual one. You should also adapt the step sizes. Every weight should have its own step, at least every weight should have its own step size, which step size is sometimes called a learning rate, but it's the amount by which you move each weight. And so I'm claiming we want the ability to learn at different rates. Learn faster in some weights and slower in some weights. And that this is how we will get to sculpt our generalization. Is that confusing? Like if you have a feature that has a large weight, then, a large step size, then you will change its weight a lot when that feature is present. And that means you'll generalize a lot along that feature. Or the other way, if that feature has a 0 step size or very small step size, then you will not generalize based on that. Does that sound good? Does that sound bad? You don't generalize? No. In a continual learning, in an agent like me or you, there are lots of things that we know that we don't want to learn. We don't want to change them anymore because they're just very reliable. We've learned for large parts of our life. We don't want to change those. And we don't want to change those because there are other things we do want to change. We are actually very skilled at assigning credit to features that are most likely to be relevant. And one way to do that is by having different step sizes for different weights. In principle, I'm thinking that in principle, if we could do that, we'd get a whole lot of desirable things, including generalization. Okay, and then the third area we'd like to adapt is the connection between the units. But this is sort of a starting view of the goal for a better learning algorithm than regular backprop or continual backprop. Okay, there are lots of questions, and I'd like to get a couple more.
We are running out, like we're already above the time, so
It's true.
there is going to be an extended Q&A now. We can keep on these questions if you guys want to ask, but I want to free people who might have other commitments. So quickly, so our next seminar will be, actually, Maxim, you knew better the date. Was it 18th or when was that? Of November?
18th.
So we'll be with Gary Kathanstev, Head of Quantum Technology at Bloomberg from New York. We hope to see many of you there as well. Know that we also have a reading group. If you want to dive more into, especially in reinforcement learning, that's what we're focused on, please come to say hi. And also, one of the sponsors, Iconic, is having some opening for master student internships. So it's on video games, AI, and reinforcement learning and stuff. So if you're interested, also come to speak to us. And that's all from my end. Free to go. Well, big.